Okay, so for this lesson we're going to take a look at some prime factorization. There's really two ways of carrying this out. We can do prime factorization with either a factor tree, or we can do division by primes. So let's take a look at an example. Let's start with, say, 420. If we wanted to do this with, say, a factor tree, and there's lots of ways we can do this, but we need to come up with two numbers that when we multiply them together would give us 420. Now when I see a number like 420, I see that it ends in a 0, so that immediately tells me that 10 is a possible factor, and 10 times 42 is what gives us 420. If I then go and break those numbers down, I have 2 and 5, which give me 10. And I can then break down 42 into 6 and 7. Now one thing I want to look at here is if any of these are prime numbers at this point. Well, if I look at the 2, I can tell it's a prime because the only factors for 2 are 1 in itself. I know 5 is a prime also because the only factors of 5 are 1 in itself. And the same thing with 7. It's a prime number also because I still have factors of only 1 and 7 for it as well. Well, that still leaves me with this 6 to break up into a pair of factors. And 6 is going to be, 2 times 3. And those are both going to be prime numbers. So we mark both of those. So now I look at the list of primes that I have. I have a pair of 2s, a 3, a 5, and I have a 7. Now we're not quite done yet. We have done our factor tree and we've got our prime numbers listed, but now we need to write this out as a prime factorization. And really there's two ways we can go about doing this. We can write 2 times 2 times 3 times 5 times 7, or if we want to use exponents to express our prime factorization, we can write 2 squared times 3 times 5 times 7. And that also works because I have 2 2's, 2 times 2, so that's 2 squared times 3 times 5 times 7. Keep in mind it's usually a good idea to write all of our factors in order numerically. This will help a lot with some of the reducing of fractions as well as the greatest common factors that we'll do later on. Another way that we can do the prime factorization of these numbers is kind of the method I prefer to use, which is division by primes. So if we start with the same number again, and I'm going to write it down here this time. I start with 420. I want to think about what prime number I can divide into 420. Well, this is going to be an even number because it ends in a 0. So we could always start with 2. You might think a little bit bigger though, because this is 42 here, the first two digits. So we know it's going to be divisible by 7. So I might just go ahead and start with 7 in this case. And if I divide 7 into 420, that's going to give me 60. We then want to divide 60 again by another prime number. Well, if I take a prime number and divide that into 60, let's say 3 this time. We could have went with 2 or even 5, but 3 goes nicely into 6 and leaves us with 20. And if we want to divide 20, let's say 2. That leaves us with 10. We're going to divide 10 by, let's say, 5. And that leaves us with 2. 2 can be divided by 2, and in the end, we are left with 1. I think it's always a good idea to divide until you are actually left with 1, because when you get to the end of the division, if you're left with 1, then you know there's a very good chance that you've got all your prime numbers. As you can see, if we look here, we've got all of the same prime numbers all accounted for. And again, if we would list them out, we're going to get the same prime factorization again. So once again, if we write those down, we're going to get 2 squared times 3 times 5 times 7. And we wouldn't really expect that to change. We would expect that to be the same no matter which way we did the prime factorization. Now let's look at something that's a little bit different. We're going to take a look at something, well, it's using prime factorization, but we're going to use prime factorization now in order to come up with the greatest common factor of two numbers. Let's start with two numbers. We're going to choose 36 and 60. What we're going to do is we're going to write out the prime factorization of both of these numbers. And once we've got that done, we're going to use that to come up with the greatest common factors of the two numbers. Now if I have 36, I want to write out its factorization first. Well, mentally I can divide this out by doing division by primes. And I know 36, I can divide that by 2, which leaves me with 18. 18, I can divide again by 2. That leaves me with 9. 9 can be divided by 3, which leaves me with 3 again. 60 is kind of the same thing. I can again divide mentally by primes. 60 can be divided by 2, which leaves me with 30. 30 can be divided by 2 also. Now I have 15. 15 I can divide by 3, which leaves me with 5 as my last factor. Now what we want to do is take a look at our factorizations, and we want to mark shared factors. That means if we look at the factorizations, what numbers do 36 and 60 share? Well, I see here I got a pair of 2's, another pair of 2's, and right here I have a pair of 3's. So if I write down these pairs, I got a pair of 2's, another pair of 2's, and a pair of 3's, and I multiply those. I take 2 times 2, that's 4, times 3 is 12. 12 is the greatest common factor of 36 and 60. So that's how we can solve for the greatest common factor using prime factorizations. We first list out the factorizations of both numbers. We mark common pairs, writing them down. We multiply, and then that in the end gives us our greatest common factor. So this has been again a lesson on how to do factorizations with either a factor tree or doing division by primes, and how we can use factorization to come up with the greatest common factor of a pair of numbers. Thanks for watching.